What we're going to learn about next is the rest of section 19.3, which has to do with locating the epicenter of the earthquake. So we're going to go through how you would figure out where that earthquake took place. And in a couple of days, we'll be doing an earthquake lab, so you actually get to do that, or at least follow along as I do that, by hand. Of course, now that would typically be done with a computer, but it's still kind of neat to see how it works. Locating an earthquake. The location of an earthquake's epicenter and the time of the earthquake's occurrence are usually not known at first. However, the epicenter's location, as well as the time of occurrence, can be determined using seismograms and travel time curves. Distance to an earthquake. Just as a person riding a bike will travel faster than a person who is walking, P waves reach a seismograph station before the S waves. Consider the effect of the distance traveled on the time it takes for both waves to arrive. Like the bicyclist and the walker, the gap in their arrival times will be greater when the distance traveled is longer. Figure 19.16 shows the same travel time curve graph shown in Figure 19.9 out of section 19.2, but this time it is joined with the seismogram from a specific earthquake. The seismometer recorded the time that elapsed between the arrival of the first P waves and the first S waves. Seismologists determine the distance to an earthquake's epicenter by measuring the separation on any seismogram and identifying that same separation time on the time travel graph. The separation time for the earthquake shown in Figure 19.16 is 6 minutes. Based on travel times of seismic waves, the distance between the earthquake's epicenter and the seismic station that recorded the waves can only be 4,500 kilometers. This is because the known travel time over that distance is 8 minutes for P waves and 14 minutes for S waves. Farther from the epicenter, the gap between the travel times for both waves increases. So if you've got one of these graphs, you have to know the lag time, or the time between the S waves and the P waves. So you're looking for where is the red line and the P and the blue line a certain distance apart. So if your interval is 6 minutes, it has to be the P wave arrived at 8 minutes and then the S wave arrived at 14 minutes, because this is the only spot where the distance between those two lines, or the time between those two lines, is 6 minutes. So it's about matching up the lag time with the distance, which is right down here. So when the lag time is 6 minutes, the distance was about 4,500. Seismologists analyze data from many seismograms to locate the epicenter. Calculating the distance between an earthquake's epicenter and a seismic station provides enough information to determine that the epicenter was a certain distance in any direction from the seismic station. This can be represented by a circle around the seismic station with a radius equal to the distance to the epicenter. Consider the effect of adding data from a second seismic station. The two circles will overlap at 2 points. When data from a third seismic station is added, the rings will overlap only at 1 point, the epicenter, as shown in Figure 19.17. Time of an earthquake. The gap in the arrival times of different seismic waves on a seismogram provides information about the distance to the epicenter. Seismologists can also use the seismogram to gain information about the exact time that the earthquake occurred at the focus. The time can be determined by using a table similar to the travel time graph shown in Figure 19.9. The exact arrival times of the P waves and S waves at a seismic station are recorded on the seismogram. Seismologists read the travel time of either wave to the epicenter from that station using graphs similar to the one shown in Figure 19.9. For example, consider a seismogram that registered the arrival of P waves at exactly 10 a.m. If the P waves traveled 4,500 kilometers and took 8 minutes according to the appropriate travel time curve, then it can be determined that the earthquake occurred at the focus at 9:52 a.m. Seismic belts. Over the years, seismologists have collected and plotted the locations of numerous earthquake epicenters. The global distribution of these epicenters reveals a noteworthy pattern. Earthquakes' locations are not randomly distributed. The majority of the world's earthquakes occur along narrow seismic belts that separate large regions with little to no seismic activity. As shown in figure 1918, earthquakes occur in narrow bands. The location of most earthquakes corresponds closely with tectonic plate boundaries. In fact, almost 80% of all earthquakes occur on the Circum-Pacific Belt and about 15% on the Mediterranean-Asian Belt across southern Europe and Asia. These belts are subduction zones, where tectonic plates are colliding and one plate is forced to sink beneath another. Most of the remaining earthquakes occur in narrow bands along the crests of ocean ridges, where tectonic plates are diverging.